Welcome back to the Deep Dive. We're the show that, really tries to cut through the noise and get you those insights that make you feel properly informed. Have you ever been there? You're trying to pay for something online, maybe something small, or just sending a bit of money to a friend, and it's just slow. Or the fees seem way out of whack for what you're sending. It's super common, right? Well, today we're diving into something really groundbreaking that promises to, well, change all that. The Lightning Network. Imagine payments that aren't just instant and dirt cheap, but also private, even for really tiny amounts like microtransactions.
That's exactly the goal. The Lightning Network, it's what we call a second layer protocol. It sits right on top of Bitcoin. And its whole purpose is basically to massively boost what Bitcoin can do. We're talking secure payments, super low cost, almost instant, and crucially, much more private than you typically get right on the main Bitcoin blockchain. For this deep dive, we're leaning heavily on, honestly, the definitive guide, Mastering the Lightning Network by Andreas Antonopoulos, Ololuwa and Rene Picard. It's pretty comprehensive.
So our mission today for you listening is to really break down the Lightning Network. Make it clear we're not just scratching the surface here. We want to pull out the really important stuff, the core ideas, the clever crypto tricks it uses, how it actually works in the real world, and yeah, even look at where it might be going next. Prepare for some of those aha moments, the kind that leave you feeling genuinely clued in about this frankly critical innovation in crypto. And hey, as we go through this, if you feel like you need a quick refresher on some Bitcoin basics, the underlying stuff, a really great accessible place to check out is bitcoinbytes.org, bitcoinbytes.org. They've got excellent summaries that really complement what we're talking about today.
Definitely a good resource. So, okay, to really get why Lightning was needed, like why it became almost essential, we have to talk about Bitcoin's scaling problem. At its heart, Bitcoin is this globally copied public ledger, right? Every single transaction, big or small, $1 million or 5 cents, it gets checked and stored by basically every computer, every node on the network.
Right.
And you can imagine that's a ton of data. Every node has to handle it, store it. And that design, well, it inherently limits how much the network can handle. Scalability becomes a real issue.
Okay, so if that's the bottleneck, the obvious question everyone asks is, well, why not just make the blocks bigger? More space, more transactions, lower fees. Sounds simple.
It sounds simple, yeah.
Yeah.
And it's an intuitive thought.
Yeah.
But when you dig into it, like the source material really lays out, it's way more complicated. It's not just changing a number. It involves these fundamental trade-offs. Sure, bigger blocks might lower fees temporarily, maybe, but it just pushes the costs somewhere else.
Somewhere else, like onto the node operators.
Exactly. Suddenly, if blocks are huge megabytes, gigabytes, even running a node needs way more internet bandwidth to download them, more CPU power to check everything inside, and just vastly more disk space to keep the whole history. So what happens?
Well, I guess running a node gets really expensive.
Right. Too expensive for your average person.
Yeah.
So only big companies, data centers, people with serious resources could afford it.
And that kind of defeats the purpose of Bitcoin, doesn't it? If regular people can't run their own node, they have to trust these big players to tell them what the ledger says.
Precisely. You nailed it. That reliance on others completely undermines Bitcoin's core idea. The whole point is not having to trust intermediaries. You should be able to check the whole thing yourself. If cost makes that impossible, the network starts to centralize.
Yeah.
And then you're right back to having single points of failure, the exact thing Bitcoin was trying to get away from.
Wow. Okay, let's put some numbers on that. Visa, right. At peak times, they handle something like, 40,000 transactions a second? It's massive.
Yeah, it's huge. Now imagine Bitcoin trying to match that with its current 10-minute block schedule. The math shows you'd need blocks around 8 gigabytes in size. Every 10 minutes.
8 gigabytes
Bro.
every 10 minutes. That's unthinkable for a regular computer setup.
Totally untenable for most people. You'd need serious hardware, serious bandwidth. It would push the network towards extreme centralization, no question. And remember, that's just matching Visa. What about all the new kinds of payments people are talking about? Machine-to-machine stuff, tiny microtransactions for like streaming data or paying per article view? The demand could be even higher.
So this fundamental problem, this tension between wanting global scale but needing to keep it decentralized, that's the real motivation for Lightning.
That's the core driver.
Yeah.
Lightning is this ingenious answer. How do we get massive scalability with tons of transactions off the main blockchain without clogging it up, but without sacrificing the security that Bitcoin provides? It's trying to get the best of both.
Which brings us to this term you hear all the time in crypto, trustless. It's often used for Bitcoin and for Lightning too. But it always sounds a bit weird, doesn't it? Like, isn't trust good?
It's a great point. And yeah, trustless can be confusing. It doesn't really mean there's no trust involved or that everyone's expected to be shady. It means you don't need to blindly trust the other person to do the right thing. The system is built so that cheating is either impossible or just really, really irrational and costly.
Yeah.
So maybe trust minimized is a better way to think about it.
Ah, okay. So you're not trusting the person, you're trusting the rules, the code.
Exactly. Think about regular banking. You have to trust your bank, the payment processors, right? You trust them to hold your money, move it correctly, not misuse their power. And if they mess up, well, good luck sorting it out quickly or cheaply. They're single points of failure. In decentralized systems like Bitcoin and Lightning, that trust shifts. It moves away from institutions, from people, onto the protocol itself, its design, its math, its cryptography. That's what you trust, because you, or anyone, can verify it works as claimed.
That shift is huge, trusting verifiable code instead of institutions. That's fundamental to understanding the security here, for both Bitcoin and Lightning.
Absolutely.
Yeah.
And the way these systems achieve that trust minimization, fundamentally, is through something called fairness protocols. It sounds a bit formal, but it's basically the engine of decentralization. A fairness protocol is just a really cleverly designed process. It uses incentives, rewards, and disincentives penalties to make sure things turn out fair between people who don't necessarily trust each other. And crucially, there's no central boss making sure everyone plays nice.
So it's less about forcing fairness and more about setting up the game so that being fair is just the smartest move for everyone involved. The rules only need to stop people breaking the protocol, not force them to want a fair outcome.
You got it. The protocol makes cheating or being dishonest way more costly than any potential gain. So being honest becomes the rational, self-interested thing to do. There's a great simple example, maybe painfully familiar to parents, the split and choose dilemma. Imagine two kids and let's say a plate of French fries or chips, depending on where you are.
Oh, the chip wars. I remember those. I bet the authors of the book remember them too, even if they joke about it being coincidental.
Huh? Probably. So the sort of naive, centralized way is the parent tries to divide the chips fairly themselves. They act as the trusted third party.
Yeah.
What happens? Always complaints, right? Shabor, that's not fair. The parent tries their best, but it just leads to arguments.
Yeah, the parent ends up being the referee. It takes all the heat and nobody's really happy. It's messy.
Exactly. But there's a simple protocol. One kid splits, the other kid chooses. Instantly fairness emerges. Why? Because the kid doing the splitting knows if they make one pile obviously bigger, the other kid is going to immediately grab that bigger pile. So the splitter's own self-interest forces them to make the split as absolutely equal as they possibly can.
That's brilliant, actually. It's not about trust or being nice. It's just rational self-interest channeled by a smart rule. A perfect little piece of game theory.
It really is. And these fairness protocols, whether it's simple like splitting chips or complex like Bitcoin, they're built using basic tools we call security primitives. These are like the cryptographic building blocks. Two really key ones are, first, strict time ordering, meaning you can prove action A happened before action B, and that order can't be changed. Second is commitment with non-repudiation. This means someone can commit to something, like digitally signing a message, and they can't later deny they did it.
Okay, so digital signatures fit right in there. They prove who signed something, you can't deny it, proves you own the key. And things like encryption, that's a primitive for controlling who sees information. These are the Lego bricks for building trustless systems.
Well put. And Bitcoin's own consensus mechanism, proof of work, POW, is a huge example of a fairness protocol. Miners spend real resources, electricity, computing power doing this work to validate transactions and create blocks. The incentives are clear. Find a valid block following all the rules, you get the block reward and the transaction fees. Big incentive.
And the disincentive, what stops them cheating?
Simple. If they try to cheat, make an invalid block, break the rules, all that electricity, all that work is just wasted. They get nothing. Zero reward. So again, no police force needed. The protocol itself makes being honest the most profitable strategy. It channels that self-interest into securing the whole network. And by the way, if you want to really understand proof of work and mining concepts better, bitcoinbytes.org, that's bitcoinbytes.org, has some great explanations. It's worth checking out for those fundamentals.
That's a really strong point. This pattern fairness coming from rules that reward honesty and punish cheating, it's exactly how Lightning works too. It's all game theory. Okay, let's finally unpack Lightning itself. How does it actually work? Starting with the absolute bedrock, payment channels.
Right. Payment channels are the core. Think of a payment channel like a private direct financial link, maybe like a running tab, between two Lightning nodes, just two participants. This tab lets them send Bitcoin back and forth, potentially thousands or millions of times, without needing to tell the main Bitcoin blockchain about every single little payment.
Okay, a private tab. How do you actually set one up? What's the mechanics?
It's pretty clever. Uses some standard Bitcoin features.
Yeah.
First, they create a special address on the Bitcoin blockchain called a 2 of 2 multi-signature address. 2 of 2 just means both participants, let's call them Alice and Bob again, each get one private key for this address. And both keys are needed to sign any transaction spending money from that address. They have joint control.
Got it. So one person can't just empty the pot.
Exactly.
Hmm.
Then they need to fund it. They create what's called a funding transaction to send some Bitcoin, maybe just from Alice, maybe from Bob, maybe both, into that shared 2 of 2 address. Now, this funding transaction does get broadcast to the main Bitcoin blockchain. It's a public record that this channel now exists and how much Bitcoin is initially locked into it. That's the channel's capacity.
Okay, funding transaction on chain. Channel is open. Now, this is the part that always bends my brain a bit. They don't send tiny transactions back and forth on chain, right? They use these pre-signed commitment transactions.
That's the magic, yeah. Instead of broadcasting every payment, Alice and Bob continuously update the state of their channel privately. They do this by creating and signing, but not broadcasting, these special Bitcoin transactions called commitment transactions. Think of them like maybe like signed checks that you both agree on, but you don't cash them yet, or like updating a legal contract privately. Each commitment transaction is a fully valid, signed Bitcoin transaction. It says, okay, if we were to close the channel right now, Alice gets X amount and Bob gets Y amount from our shared 2 of 2 address. They create a new one every time the balance shifts. And crucially, only the latest one reflects the true current balance. Either Alice or Bob can, at any time, take the latest commitment transaction they both agreed on and broadcast that to the Bitcoin blockchain to settle up and close the channel.
And this whole system, these off-chain updates, relying on a final settlement transaction, it heavily depended on the segregated witness, or SegWit, upgrade to Bitcoin in 2017, didn't it? There's this issue called transaction malleability before SegWit.
Oh, absolutely critical. SegWit was essential. Before SegWit, there was this weird quirk where someone could slightly change the way a transaction signature was encoded without invalidating the signature itself. It didn't change who owned the funds, but it did change the transaction's unique ID, the TX ID.
Okay. Why was that a problem for Lightning?
Imagine Alice has a pre-signed transaction ready to go, maybe a refund transaction, that specifically refers to the TX ID of the original channel funding transaction. If that funding transaction's TX ID got malleated, changed slightly before confirmed, Alice's pre-signed refund transaction would suddenly become useless. It's trying to spend funds from a TX ID that technically doesn't exist anymore on the blockchain. This made building reliable second layers like Lightning incredibly risky, almost impossible, because you couldn't depend on the IDs of unconfirmed transactions.
So SegWit fixed that by basically making the TX ID stable once signed.
Exactly. SegWit restructured transactions to separate the signature data, the witness, from the main transaction data used to calculate the TX ID. This meant the TX ID became fixed and immutable from the moment it was signed, even before confirmation. That stability was the green light Lightning needed. It guaranteed that those pre-signed commitment transactions would remain valid. Without SegWit, honestly, Lightning probably wouldn't exist in its current form. It was a massive unlock.
Okay, so channel's open, SegWit's fixed malleability. Alice pays Bob inside the channel. They create a new commitment transaction reflecting the new balance. What stops Alice from trying to broadcast the old commitment transaction later, trying to pretend she didn't pay Bob?
This is where the real genius, the cryptographic enforcement, comes in. It's the revocation secret mechanism. It's core to Lightning security. Every time Alice and Bob agree on a new channel state, a new commitment transaction, they invalidate the previous state. They do this by exchanging a special piece of secret data, a revocation key or revocation secret specifically linked to that old state.
Okay, so they swap secrets for the state they just replaced. How does that stop cheating?
Let's say Alice does try to cheat. She broadcasts an old, revoked commitment transaction where she has more money. Bob sees this happen on the Bitcoin blockchain. Because he has the revocation secret for that specific old state, he can immediately create and broadcast a special penalty transaction.
Yeah.
This penalty transaction uses the revocation secret to basically sweep all the funds in the channel Alice's share and Bob's share entirely to Bob.
Wow. So if you try to cheat with an old state, you don't just fail, you lose everything in the channel.
Everything. It makes attempting to cheat utterly counterproductive. The penalty is so severe that rational participants are strongly incentivized never to broadcast an old state. They always cooperate using the latest state. It's pure, beautiful game theory enforced by cryptography. No need for a judge or arbiter.
That is incredibly clever, a self-enforcing digital contract. Okay, so eventually people do want to close channels. What are the ways that happens?
Right, closing the channel. There's the good way, the bad way, and the ugly way. Sort of. The mutual close is the good way. Alice and Bob are cooperating. They agree on the final balance, they both sign a single closing transaction reflecting that balance, and they broadcast it together. It's usually quick, cheap, just one on-chain transaction, and settles immediately.
Makes sense. What if Bob isn't responding? Maybe his node is offline.
That's where the forced close comes in the bad way, but sometimes necessary. If Alice needs to close the channel and Bob is offline or uncooperative, Alice can take the latest valid commitment transaction they both signed and broadcast it herself. But there's a catch. To protect Bob, Alice's funds from that force-closed commitment transaction are usually locked for a period, a time-lock delay, maybe hours or days. This gives Bob time to come online, check the blockchain, and if Alice broadcasts an old state, Bob has that window to use the revocation secret and broadcast the penalty transaction.
Ah, the time lock is Bob's safety net during a forced close. And the ugly way.
The ugly way is a protocol breach. That's when Alice maliciously force closes, using an old, revoked commitment state, deliberately trying to steal funds, hoping Bob isn't watching. This is exactly why your node needs to be online monitoring the blockchain, or you need to use a watchtower.
Watchtowers, what are they?
A watchtower is basically a service could be run by a third party, or even another node you run yourself that you give encrypted information about your channels. It constantly watches the blockchain for you. If it detects someone trying to broadcast an old revoked state against one of your channels while your main node is offline, the watchtower can automatically broadcast the penalty transaction on your behalf using the revocation info you gave it. It's a crucial safety mechanism, especially for mobile wallets or nodes that aren't online 24/7.
Okay, that covers channels between two people,
Yeah.
but the real power comes from routing payments across multiple channels, right? Alice paying Dina through Bob and Chan, even if Alice and Dina don't know each other directly. This uses hash time-locked contracts, or HTLCs.
Exactly. HTLCs are the engine that drives routing across the network. They're a special type of smart contract built using Bitcoin script. An HTLC combines two conditions, a hash lock and a time lock. The hash lock means funds locked in the HTLC can only be claimed if you reveal a secret piece of data called the preimage. The time lock means if that secret isn't revealed before a certain time, the funds automatically return to the person who sent them. These two together allow for trust-minimized routing.
Okay, a lock based on a secret and a deadline. How does that kick off a payment?
It starts with the receiver, Dina. She generates a random secret number, let's call it R, the preimage. Then she calculates its cryptographic hash, let's call that H, the payment hash. H actually is like the public lock. Dina puts H in her payment request, like an invoice, and gives it to Alice. Dina keeps R, the secret key, to herself for now. To get paid, someone needs to eventually reveal R.
Got it. Dina makes the lock H, keeps the key R. Alice gets H and wants to send, say, 50,000 Satoshis to Dina, but they need to go through Bob and Chan. How does the HTLC chain work?
Okay, let's trace the 50K Satoshis. Alice minus Bob minus Chan is Dina, 1-5. Alice offers an HTLC to Bob in their channel. It locks 50,000 sats, plus maybe a tiny fee for Bob. The condition: Bob can claim this if he provides the secret R matching hash H before time T1 expires. If not, Alice gets it back. 2. Bob sees this incoming HTLC. He doesn't know R, only H. He then offers an HTLC to Chan in their channel. He locks 50,000 sats plus maybe a fee for Chan. The condition: Chan can claim this if he provides R matching H before time T2 expires. Crucially, T2 is earlier than T1. Bob needs time to get R from Chan and still claim from Alice before his deadline. 3. Chan does the same with Dina, offers an HTLC for 50K sats lock of HE, needing R before time T3, which is even earlier than T2. 4. Dina gets the HTLC from Chan. She knows R, so she reveals R to Chan and claims the 50K sats from him just before time T3. 5. Now Chan has R. He immediately uses it to claim the funds from Bob just before time T2 expires. 6. And Bob now has R. He uses it to claim the original 50K sats from Alice just before T1 expires.
So the secret R flows backward, Dina, Chan, Bob, Alice. And the funds effectively flow forward, Alice, Bob, Chan to Dina. And each intermediary, Bob, Chan, takes their small routing fee.
That is slick. So Bob and Chan never need to trust anyone. They just need to trust the crypto that R matches H and the time locks. If the payment works, they get R and claim funds. If it fails, the time locks expire and everyone gets their locked funds back. And they own a fee for facilitating.
Precisely. It's completely trust minimized. No intermediary holds the funds riskily. They just lock liquidity conditionally. This lets the network scale out massively, connecting everyone through chains of these channels.
Amazing. Okay, one more core piece. Privacy. Bitcoin's not very private on chain. How does Lightning handle privacy when payments hop across nodes? You mentioned onion routing.
Yeah, Lightning uses an onion routing protocol, similar conceptually to Tor, called the SFIN-X format. It encrypts the payment instructions layer by layer for each hop. The nested envelopes analogy works really well here.
Walk me through the envelopes again. Alice paying Dina via Bob and Chan.
Okay, Alice wants to send the payment details, amount, #H, secretly to Dina. 1. Alice takes the core message for Dina and encrypts it using Dina's public key. That's the innermost envelope. Only Dina can open it. 2. Alice then takes that encrypted Dina envelope, adds instructions for Chan, like send the inner thing to Dina, and encrypts all of that using Chan's public key. Now it's a Chan envelope containing the Dina envelope. 3. She does it one more time. Takes the Chan envelope, adds instructions for Bob, send the inner thing to Chan, and encrypts that whole package using Bob's public key. This is the outermost envelope she sends to Bob. 4. Bob receives it. He uses his private key to decrypt just his layer. All he sees are the instructions. Send this inner encrypted blob to Chan. He doesn't know it came from Alice originally, or that it's ultimately going to Dina, or how many more hops there are. He just knows the previous hop, Alice, and the next hop, Chan. 5. Bob sends the inner blob to Chan. Chan uses his key, decrypts his layer. He sees, send this inner encrypted blob to Dina. Again, he only knows Bob and Dina. 6. Chan sends the innermost blob to Dina. Dina uses her key, decrypts it, and gets the original payment info from Alice.
Like peeling an onion, layer by layer. Each person only sees their instructions and the next step. That provides pretty strong privacy from the intermediaries.
It does. Key features. Intermediaries only know their immediate predecessor and successor. They don't know the total path length or their position in it. This makes it really hard for any single routing node to figure out who the original sender and final receiver are. And even if something goes wrong, error messages are also onion routed back along the path, preserving privacy even during failures.
That's a seriously clever design. Okay, we've covered the why and the how of Lightning's core mechanics. Now, for people listening who are thinking, okay, I want to use this, or even run a node. Now, let's get practical. What about Lightning node software and wallets?
Right. One interesting thing about Lightning is that, unlike Bitcoin, where Bitcoin Core is the clearer reference, Lightning has multiple independent but interoperable implementations. You've got ALEND, written in Go, C Lightning and C Eclair in Scala. They all speak the same Lightning language. They follow the BOLT standards, basis of Lightning technology, so they can talk to each other. But having different teams builds resilience and spurs innovation. You can pick based on features, language, or community.
And the term Lightning Wallet, it seems to cover a lot of ground.
It really does. A Lightning wallet could be just a simple app on your phone, or it could be a full-blown setup with the Lightning node software, a Bitcoin node, channel management tools, pathfinding, the whole 9 yards. The most important distinction for you as a user is custodial versus non-custodial. You'll hear this a lot. Not your keys, not your coins.
Non-custodial means I hold my own keys, right? Like my own bank.
Exactly. Non-custodial means you control the private keys, usually stored securely on your device. You don't rely on anyone else to hold your funds. Maximum security, maximum sovereignty. Custodial wallets are easier, often feel like using Venmo or PayPal, but the company holds the keys for you. You're trusting them completely. They're convenient, maybe a good first step for some, but you give up control and face counterparty risk. They're really just IOUs for Bitcoin on Lightning.
And some wallets might mix and match, maybe run the wallet interface locally but connect to someone else's node.
Yes, that happens too. You might run a non-custodial wallet app, but it connects to a remote Lightning node run by the wallet provider, or even a remote Bitcoin node. Each component you outsource trades convenience for trust. The ideal, from a purist perspective, is running everything yourself, but that's not always practical for everyone.
Let's take Alice again for mastering Bitcoin. She wants to buy coffee from Bob's Cafe using Lightning. The source mentions she picks Eclair, a non-custodial mobile wallet. How does she get started?
Okay, first step. Get some Bitcoin into her wallet. Buy it on an exchange, get paid in it, use an ATM, whatever. Load it into Eclair. Then she needs to connect to the Lightning network itself. She needs to open a payment channel.
Does she need to open a channel directly with Bob's Cafe?
Nope. That's the beauty of routing. She just needs to open a channel with someone who is reasonably well connected on the network. Her payment can then hop through the network to reach Bob's Cafe. Wallets like Eclair often make this easy. They might suggest opening a channel with a random well-connected node, or maybe with a large public node run by the company itself, like the ACINQ node in Eclair's case. This gets her bootstrapped onto the network quickly. Think of it like getting onto the main highway system.
Okay, so that's using Lightning. What about actually running a node? Being part of the infrastructure? Maybe you run a shop, want to earn routing fees, or just support the network. What does that involve? And it's
Yeah.
different from just running a Bitcoin node, right? Reliability is key.
Huge difference, yes. Reliability is paramount for a Lightning node. A Bitcoin node can go offline and just catch up later when it comes back online. It can still receive transactions sent while it was offline. A Lightning node, however, needs to be online, ideally 204/7. Why? To send payments, to receive payments in real time, and crucially, to route payments for others. If your node is offline a lot, well, you can't receive money. Payments routed through you will fail. Your channel partners might close channels with you because you're unreliable and tying up their capital. And worst case, you could miss a cheating attempt if a partner tries a malicious forced close while you're offline, unless you have a watchtower set up.
So my laptop that I turn off every night is probably not the best choice for running a serious Lightning node.
Definitely not ideal. Laptops and desktops compete for resources. They get rebooted. For 2 for 57 operation, people usually go for dedicated hardware. Popular choices are things like a Raspberry Pi 4 with enough RAM, like 4 GB or 8 GB, or maybe a small Intel NUC mini PC. They're low power, can sit in a corner running constantly. Or you can run a node on a cloud virtual private server, VPS, that gives you high uptime and good connectivity, but you're trusting the cloud provider to some extent. Hardware specs. You want maybe a 2-4-core CPU, RAM, minimum 2 GB, but honestly 4 GB or more is better, especially for syncing. And storage is important. You need a fast SSD solid-state drive, at least 512 GB, ideally 1 TB. The Bitcoin blockchain alone is around 360 GB and growing fast, and the SSD speed is crucial for syncing and database operations.
And for setting it all up, is it super technical, command line only?
It can be, but there are much easier options now. There are fantastic projects like MyNode, Umbrel, Raspablitz. These are basically prepackaged software bundles, often with really nice web interfaces. They install Bitcoin Core, your chosen Lightning implementation like LND or C Lightning, and manage it all for you. Umbrel, for example, is known for its slick UI. It even uses a trick called SPV initially, so you can start using Lightning almost right away while the full Bitcoin blockchain downloads in the background, which can take days. And then there's BTC Pay Server. If you're a merchant, it's amazing. It's an open-source payment processor, but it also includes easy-to-install Bitcoin and Lightning nodes, usually using Docker. Very powerful.
Once you have the hardware and maybe one of these installer helpers, you still need to configure the Bitcoin node part, right? Full node, pruned.
Yeah, you need a Bitcoin node for your Lightning node to talk to. Usually it's Bitcoin Core, the reference, or maybe BTCD, a Go version. Then the big decision is archival versus pruned. An archival node keeps the entire history of all Bitcoin transactions. Over 350 gigalubi now, growing daily. This is the best for the network's health and decentralization. A pruned node downloads and verifies the whole chain initially, but then deletes older blocks to save disk space, maybe keeping only the last few gigabytes. It saves space long-term, but might have limitations for some advanced Lightning features, and it's still kind of experimental for some setups.
So the recommendation is,
If you can swing it, if you have that 500 gigabyte or 1 TB SSD, run a full archival node. You contribute more fully to Bitcoin's robustness. If disk space is tight, pruning is an option. Just be aware it's a slight compromise. There are also even lighter options like Neutrino for LND, which rely more on remote nodes, trading off some trust for minimal local storage.
hey, here's the big scary part, security. A Lightning node is a hot wallet. The keys controlling your funds are online. That's inherently risky. How do you manage that?
Critically important point. Rule number 1, do not keep your life savings on your Lightning node. Seriously, it's a hot wallet, like the cash in your physical wallet. Keep significant amounts in cold storage hardware wallets, paper wallets, offline. Your Lightning node should only hold funds you're actively using for payments and channel capacity, an amount you could afford to lose, however unlikely. If the balance gets too high, maybe you run a popular routing node or shop and shop, you need to periodically sweep funds out to safety.
How do you sweep funds?
Few ways. On-chain sweep. You close some channels, mutually if possible, force close if needed. The Bitcoin comes back to your on-chain wallet, and you send it to your cold storage address. Downside. Costs on-chain fees, reduces your channel capacity temporarily. Off-chain sweep. If you run a second, private, unannounced Lightning node, maybe super secure, you could just make a large Lightning payment from your public hot node to your private node. Keeps funds off-chain, but moves them to a safer hot wallet. Loop out. This uses a service called a submarine swap. You send Lightning funds to the service, and they send you back on-chain Bitcoin to your cold storage address, minus fees. It's a popular way to rebalance or move funds to cold storage without closing channels.
And watchtowers play a role in hot wallet security, too.
Absolutely. They're your insurance against your node being offline during a cheating attempt. By having a watchtower monitor your channels, you gain significant protection against malicious forced closes, even if your own node isn't watching 24/7. Essential for mitigating hot wallet risk.
What about just basic server security, the computer running the node?
Standard best practices are vital. Verify software sources. Make sure you're downloading legit code. Use strong authentication SSH keys instead of passwords for access. Use two-factor auth, 2FA, wherever possible. Regular encrypted backups are a lifesaver. Backup your node's data and your channel state backups, SCBs. Minimize the attack surface. Turn off any services you don't need. Close unnecessary network ports. Don't browse the web or check email on your node machine. Keep it dedicated. And protect access to the node's control interface, RPC. Use strong random passwords or, better yet, authentication mechanisms like macaroons, which provide more granular, limited permissions.
Okay, last piece for setup. Connectivity. For a node to route payments, people need to be able to connect to it, right?
Yes. If you want to be a routing node or receive spontaneous payments easily, your node needs to be reachable from the internet. This usually means having a stable public IP address and setting up port forwarding on your home router to direct incoming Lightning traffic, usually port 9735, to your node's internal IP address. Tools like canuseen.org can help you check if your port is open. It can be fiddly depending on your ISP and router.
Is there a more private way? What about Tor?
Yes, Tor is a great option for privacy. You can configure your Lightning node, LND, C Lightning Eclair, all support it, to run its public connections over the Tor network. Your node then gets a .onion address instead of revealing your home IP address. This makes it much harder for anyone to link your node operation back to your physical location. Highly recommended if privacy is a major concern. Manual port forwarding is the alternative, but often more complex with dynamic IPs and router configs.
All right, let's shift gears a bit. Beyond just setting up, let's talk about managing a node actively in the Lightning ecosystem. Opening channels, there's some strategy there.
Definitely. You don't just open channels randomly. You want to connect to peers who are well connected themselves, who have good uptime, and who have decent capacity. Spreading your connections across several good peers gives you better routing options and redundancy. Having multiple channels also helps with larger payments, as you might need to split them using multi-part payments.
That sounds like a lot to figure out manually. Are there tools for that? Autopilots?
There are. Some nodes, like LND, have an autopilot feature. It tries to analyze the network graph and suggest or even automatically open channels to nodes it thinks will improve your connectivity. It looks at centrality, capacity, etc. C Lightning takes a slightly different approach, more like giving you recommendations that you then execute manually. Autopilots are still evolving, but they can help bootstrap a new node.
What about when channels get unbalanced? Like you send a lot out one channel, so all the money ends up on the other side?
Yet, channel rebalancing is a constant task for active routing nodes. If a channel becomes lopsided, all the funds are on one side. It can't route payments in that direction anymore. You can rebalance using services like Loopout, Submarine Swap, to push funds back to your side. Or you can do circular rebalancing, essentially making a payment back to yourself through other nodes in the network to shift funds around. Or sometimes you just wait for traffic to naturally flow the other way. Fee adjustments can also encourage flow in a certain direction.
Ah, fees. How do routing nodes make money? How do fees work?
So when your node forwards a payment for someone else, you charge a small fee. It usually has two parts. A fixed base fee, often incredibly tiny, like a fraction of a Satoshi, a millisatoshi, charged just for using the channel. And a proportional fee, charged based on the amount being routed, usually expressed in parts per million ppm. So, a 100 ppm fee means you charge 100 Satoshis for every million Satoshis routed through your channel. Nodes compete on fees. Lower fees might get you more routing volume, higher fees earn more per transaction but might get less traffic. Finding the right balance is part of the game. You can set fees per channel.
Managing all this channels, fees, rebalancing sounds like it could get complex. Are there graphical tools, dashboards?
Oh yeah, absolutely. Command line is powerful, but GUIs make life much easier. There are excellent web-based dashboards like Ride the Lightning, RTL, ThunderHub, and Spark Wallet. They connect to your node and give you a visual interface, see your channels, balances, routing history, manage fees, open-close channels, make payments, Everything.
Okay.
They really lower the barrier to managing a node effectively.
Let's circle back to privacy. We talked about onion routing, but you mentioned it's not perfect. What are the deeper nuances and risks? Anonymity sets.
Right. It's more private than on-chain Bitcoin, but not perfectly anonymous. The concept of an anonymity set is key. For any action, like making a payment, the anonymity set is the group of all possible people who could have performed that action from an attacker's perspective. De-anonymization attacks try to shrink that set. They gather clues, correlate information, trying to narrow it down until, ideally, only one identity remains.
So even with onion routing, what information can leak?
Well, intermediaries do see the exact payment amount passing through their specific channel hop. Even with multi-part payments, MPP, splitting the payment, they see the amount of their chunk. And importantly, they see the time lock values, the CLTV deltas, for the HTLCs. Also, larger payments often have fewer possible routes across the network just due to liquidity constraints. Fewer possible paths means a smaller anonymity set to begin with.
And you mentioned on-path versus off-path attackers?
Yeah. An off-path attacker just observes the network from the outside public channel data, maybe node up times. They have limited info. An on-path attacker is much more dangerous. They run one or more nodes within the payment route. They see the payment amounts and the time locks directly. By carefully analyzing the timing differences, how long it takes the payment attempt to reach them, and how long the time lock is, they can sometimes infer their position in the route, and potentially even make educated guesses about the sender and receiver, especially if they control multiple nodes along the path. Timing analysis is a known challenge.
All right, what about actively disrupting the network? Denial of service attacks.
That's a concern, too. Because failed Lightning payments often don't cost the sender anything right now. Unlike Bitcoin transaction fees, it's cheaper for an attacker to spam the network. Two main types. Commitment jamming is where an attacker initiates lots of HTLCs across a channel but never settles them, just letting them time out. This uses up the limited number of concurrent HTLCs allowed on a channel, blocking legitimate payments. Channel exhaustion or liquidity lockup is similar, but uses large value HTLCs to tie up the channel's liquidity, again making it unusable for others. These are active areas of research for mitigations.
And that cross-layer attack sounds really tricky, linking Lightning activity to Bitcoin blockchain activity.
It's a serious privacy leak potential. Attackers watch the public Bitcoin blockchain for channel opening and closing transactions. Then they correlate that with off-chain Lightning activity. For example, if they see a specific Bitcoin UTXO, an unspent coin, used to fund multiple Lightning channels, they can infer those channels likely belong to the same person or entity. Or if funds from a closed channel are immediately used to open a new channel that links them. Even things like using similar names or aliases for different nodes, mynode 1, mynode 2, can give clues. They build a profile by connecting on-chain and off-chain data.
So how do you defend against that? Be more careful with your Bitcoin hygiene.
Pretty much. Use fresh Bitcoin addresses and UTXOs for funding each channel. Don't reuse addresses. Maybe use different Bitcoin wallets entirely for funding different groups of channels to break the linkage. And consider using unannounced channels, sometimes called private channels, for links where you don't intend to route public payments, like between two nodes you own yourself. These don't get broadcast to the network graph, making them invisible to casual observers and much harder to link via public data.
It's clear Lightning is still evolving fast. What's on the horizon? Bitcoin protocol upgrades that help Lightning.
Yes, developments in Bitcoin itself are huge for Lightning. Taproot, which is already active, is a big one. It uses Schnorr signatures and makes many complex transactions, like cooperative channel closes, look just like simple single-signature payments on the blockchain. This improves privacy by making Lightning channel activity less distinguishable. Looking further ahead, there's ongoing research into things like covenants, ways for Bitcoin transactions to restrict how the funds can be spent in the future. This could enable much more powerful and secure enforcement mechanisms for Lightning channels and other Layer 2 protocols, potentially simplifying things like the penalty mechanisms.
And within Lightning itself, what protocol improvements are coming?
The protocol is designed to be extensible, using something called TLV, type length value records. This lets developers add new features without breaking older nodes. It's enabling cool stuff like path blinding, where the final hops of a route, including the recipient, can be hidden even from the sender, boosting privacy. Also, trampoline payments, which help lightweight or mobile clients send payments without needing the whole network map. The payment sort of trampolines off a known routing node that does the heavy lifting of finding the path.
What about improving payment reliability or flexibility?
Multi-part payments, MPP, is huge and already widely used. It lets you split a single large payment across multiple smaller paths simultaneously. This dramatically increases the chance of success for big payments and improves privacy since no single intermediary sees the full amount. And KeySend is another cool one. It lets you just push a payment to a node without needing an invoice first. Great for spontaneous things like tips, donations, or maybe streaming payments.
And finally, what about actual applications built on Lightning Labs?
Oh, the ecosystem is exploding there. You have LNURL, which is a standard that makes interacting with Lightning services way easier for withdrawals, logging in static payment addresses. You have Lightning addresses that look like email addresses, you at yournode.com, making it super simple to receive payments. Plus, you're seeing it used for micropayments and gaming, paying for API calls, streaming content monetization, value-for-value podcasting. It's enabling business models that just weren't feasible before with high on-chain fees.
Wow. So, okay, we've covered a lot of ground, from why Lightning is needed to the nitty-gritty of channels and HTLCs, onion routing, running a node, managing it, privacy concerns, and what's next. Hopefully for you listening, this deep dive has given you a really solid understanding of this complex but incredibly important technology. You should feel well equipped with some valuable insights now. It really feels like Lightning is pushing Bitcoin into totally new territory.
It absolutely is. It addresses that core scalability issue in a really innovative way using these clever cryptographic and game theoretic tricks.
It really makes you think, doesn't it? The Lightning Network isn't just about faster Bitcoin payments. It feels like a shift in how we think about trust and fairness and value transfer in a purely digital world. As this network grows and gets more robust, what kind of new economic interactions, what new possibilities will open up when truly instant, cheap, private, global payments are just normal? What problems get solved next? Something to ponder. And don't forget, if you want to solidify those Bitcoin basics or explore related topics, check out bitcoinbytes.org. That's bitcoinbytes.org. Thanks for joining us on the deep dive. We'll catch you next time.